In the last few years, there have been great strides in the way in which machines can handle information with the aid of microelectronics. In every field, mechanical controls are being replaced by superior and trouble-free electronic substitutes. This is the familiar old-fashioned taximeter. It was designed to measure the time taken to complete a journey and the distance traveled, and convert this information into the fare. It was all done mechanically by a complex arrangement of gears and levers. It was robust and reliable, and over the years underwent many improvements and modifications. But with galloping inflation, it became more and more useless. Every time the fares went up, the gears had to be changed in every taxi in the land, and that could take up to 6 months. A fiddling and costly business. And that's where microelectronic metering proved its worth. A meter was developed that allowed changes in the fare structure to be made in a few minutes. Passengers could see the new fare correctly and clearly displayed without having to add on the necessary increase shown on a grubby conversion table glued on the driver's window. What makes all this possible is this. It's called a microprocessor. The electronics for the meter take up very little room. At the heart of the system is a small microprocessor which does all the work. There are a number of memories which hold the instructions which tell this processor what to do and what calculations to execute. These are called read-only memories, ROMs for short. There are also memories which contain the information which has to be processed, how far the taxi's traveled, how long it's taken to do the journey. These are called random access memories, RAMs for short. Then there's the circuitry which connects the processor to the outside world, the input-output ports. One ROM contains the information about the fare tariff. If the tariff changes, you simply take out the old ROM and replace it with one holding the updated information. To make the processor work, it has to be given a series of instructions, which is called a program. This is the program telling a processor to add two numbers together. The program is held in one of the memories. The instructions are coded. The dark green numbers on the left are the actual program code. The characters on the right are the instructions. The processor has, amongst its circuits, a program counter. When this is set to the first number of the program, the processor begins working. The first instruction is drawn out of the memory and placed in the instruction register. It tells the processor that the next piece of information it receives will be, in this case, a number which should be placed in a particular register so that it can be processed later. As the program counter automatically changes, the processor opens the circuits and the information is moved. The next instruction tells the processor to draw out from the memory the next piece of information, which in this case is again a number, and to place that number in the accumulator where it's held for processing. The next instruction tells the processor to add the two numbers. The processor opens the circuits to transfer the contents of the register to the temporary register, and then passes the contents of it and the accumulator through the arithmetic logic unit, which has been activated to add. The result is then placed in the accumulator. The next instruction tells the processor to place the contents of the accumulator into an input-output port. Although this may look like a laborious way to add numbers together, it is astonishingly fast, completed in millionths of a second. In this greatly magnified and slowed down film, you can see the switching in a processor at work. The processor receives its switching instructions from the program. A program may contain many thousands of separate instructions, And writing such a program can be very complex and time-consuming. On the other hand, the instructions can be simple and straightforward, like this program for a machining center. This machining center finishes small gearboxes. The program is placed into the machine in the form of punched tape. The tape holds all the commands needed to make the machine work efficiently. The components are accurately placed on jigs, which are then fed continuously through the center. The program consists of instructions written in symbols and numbers known as a language. In this case, the language describes particular operations such as milling and also gives reference points in 3 dimensions, X, Y, and Z, where these operations are to take place. A machine like this can maintain extremely fine tolerances. The center can carry up to 19 different tools for milling, drilling, turning, and boring. Of course, the tools themselves will eventually wear, and the program is modified from time to time to take account of this. The technician can compensate by obtaining a display of the relevant part of the program, moving the cursor to the bit that has to be changed, and typing the new instruction in. The program can be altered very simply to make small adjustments, or a completely new program can be introduced to produce different components. These new microelectronic controls are being introduced in many different forms throughout industry. This machine is used for punching holes in metal plate. The precision and accuracy of the punching is unfaultable. A microcomputer controls the operation, and this means that the machine can be quickly reprogrammed to create holes of different sizes in different patterns. All the operator has to do is load the metal plate into the machine and, if necessary, change the size of the punch. On this line, the armatures of small electric motors receive their windings. The line is controlled by a number of small computers. The armatures are placed on a jig and copper wire is wound into their slots. The number of winds will change from batch to batch depending on the power of the motor. The winding machine is controlled by a microcomputer. The number of windings can be changed between batches by moving these digital thumb wheel switches. The microprocessor will then readjust the timings so that a different number of windings can be made. The processor deals only with the winding of armatures. It's a dedicated system. Dedicated, that is, to just one function. Even the smallest of tools can be adapted to microelectronic control. In this heavy-duty hand-operated drill, the power delivered by the motor is controlled by microelectronics. As the drill gradually accelerates to the full working speed, the power remains constant. Gradual acceleration prevents erratic and jerky starts. There's also a control which prevents snatch when the point of the drill breaks through the steel or whatever it's cutting. An improvement which makes the drill much safer to handle. Biscuits are made by the tens of millions. They're stamped, baked, and then wrapped. Once they're wrapped, they have to be checked to see that they're not over or underweight. This used to be done by hand, but when you're producing 1 million packets a day, this is no longer possible. As an intermediary step, electric systems were developed which would weigh the packets and reject them if they weren't acceptable. But these were simple machines. They could only weigh to the nearest gram, and if dirt accumulated on the weighing arm, the machine would produce errors. One company had the bright idea of passing the packets over suspended arms. Any dirt would just fall off. The device is controlled by microelectronics. On the circuit board, there's the microprocessor. A read-only memory, which holds the instructions. The input-output devices, which link up with the weighing machines. And circuitry linking the machine to the keyboard that controls it. The idea of using a force-balance weighbridge was simple. What was complex and difficult was developing the program for the processor. The program was written in what's called assembly language. Each instruction appears in an abbreviated form using alphanumeric characters. The difficulty lay in deciding what to take as the weight of the biscuits, because as one packet comes onto the weighbridge, the packet before it is still there. For a brief moment, there's only one packet on the weighbridge, and then it's pushed off by the next packet. This is a plot of the various weights recorded throughout a weighing cycle. The variations on the left are where a new packet is coming onto the weighbridge. The horizontal part in the center is where the packet is at rest. The variations on the right are where the cycle starts again with another new packet. So, the job of the program was to tell the processor to ignore most of the information and just record the flat piece in the middle. This is what the program did. The processor was instructed to put all the information in its random access memory, and then to look at the information until it found a run of consecutive weights which were the same, and if there was more than one run, to take the longest. This is the part of the program that deals with these instructions. It contains about 500 different commands. The program was written using a video display linked to a microcomputer. The advantage of this is that the computer allows more than one person to work at the same time, and alterations can be made quickly. The program is recorded on a floppy disk, a thin plastic circle with a magnetic coating. To put the program into the read-only memory, it has to be translated into the language which the microprocessor understands, machine language. The disk is placed into another small computer which carries out the translation. The ROM in this case is a special one used in development projects where the contents can be wiped. The computer is given its instructions to transfer the information and display the translation. This is the machine language written in an abbreviated form. The ROM can now be placed in the control unit and testing can begin. The processor, naturally, can only handle problems anticipated by the programmer. So when developing a program, it has to be checked to see that every situation has been anticipated. When snags come up, then the program has to be modified or debugged. The processor can do much more than simply weigh the packets of biscuits. It's been designed to send the results back to the computer controlling the oven. This is a display for a test run of biscuits, and some of the weights fall outside the permitted limits. That's the two horizontal lines. Light packets mean that the biscuits are overbaked. Heavy packets means they're underbaked. This information is sent back to the computer at the oven, which adjusts the temperature until perfect biscuits are once again being produced. Because microelectronics are so versatile, they're very valuable in research and development departments. In the initial design stages, sophisticated microelectronic systems can be used to produce engineering drawings of new components. Standard elements can be brought together to compose the complete layout of a drawing. In this case, it's the cylinder head of an engine. This information can be fed into a plotter to produce drawings of any desired scale. Naturally, this saves a lot of time and means that a far greater number of experimental drawings can be produced quickly for evaluation. This electric drill is being tested to see how it performs over a working life of many thousands of hours. It's switched on and off, the speed is varied constantly, and so is the workload. A microprocessor controls the relays, and the program can be changed quickly to suit any electric tool. In this case, the program is written graphically by building up various symbols of electrical circuits like switches, relays, and resistances. Whether it's a small electric motor or a huge diesel engine, the principle is the same. The engines can be taken through a multitude of cycles, and the results can be continuously monitored and analyzed by a microcomputer, and mistakes can be corrected. After testing, these engines will go into a warehouse to be stored until they're needed. This huge warehouse forms part of a unique computer information system which controls the supply of components used in the assembly of an award-winning new British truck. The idea behind it is to see that the components arrive at the assembly line on time. When they enter the factory, the details are straight away entered into the computer, which assigns them to a specific place in the warehouse. This information is passed on to another computer, which controls the scheduling of the truck assembly. Work only begins on the chassis of a truck after the scheduling computer has confirmed that all the parts needed are in stock. An order for all the parts to be brought to the assembly line in the correct sequence of priority is sent to the warehouse computer, which programs the cranes to withdraw the pallets of materials as soon as they're required. The cranes are completely automated. Trucks are custom built to individual orders, and no two are the same. This company offers 12 different combinations of engine and gearbox. And one of the first big jobs in truck assembly is the mounting of these two vital components. It takes about 5 hours to prepare the engine for final mounting in the truck. The computer arranges things so that the correct engine for the right chassis come together as if by magic, exactly the right moment on the assembly line. The foreman gives the computer the latest details of progress, and the computer decides whether to hold up delivery of the engine in a buffer zone for a few minutes or route it straight away into the assembly zone. There are about 6,000 parts used in the building of a truck. An individual printout for each truck lists every part and every variation. Many of the parts are, of course, common to all the trucks, and they're held at the assembly line in small batches. The computer works out how many of these will be used during the course of a shift, and every morning the appropriate amount is delivered at the right place. The position of every item, down to the smallest nut and bolt, is continuously monitored. The forklift driver informs the computer when he's made a delivery, and the computer automatically records that the parts have been delivered, that the warehouse stocks are correspondingly depleted, and it'll indent for stock to replace them. The size of the operation controlled by the computers is enormous. Just as each truck must have its own specific engine, so the cabs have to be fitted out and painted to the customer's specification and arrive on time at the assembly line. All the trucks are tested after assembly by courtesy of yet another computer. In its memory, it has the parameters for all the different engines, gearboxes, and wheelbases. The testing driver receives his instructions through a video display unit, and he can have a two-way conversation with the computer, answering its questions with a handheld keypad. This kind of dialogue is known as an interactive system, and it's becoming more and more common. The computer records all the playback from the driver and evaluates it. It's a system which ensures that the trucks are monitored at every stage of building. The work of assembly is speeded up, quality control is more thorough, and errors can be picked up and put right at an early stage. These microelectronic systems are being used more and more in industry, and they provide an exciting new tool to solve many problems in the design and production of a vast range of products.